Alright, simple machines, we're going to focus on levers. So right there I see a potential class 3 lever, I see a class 2 lever, and I see a class 1 lever in here. So let's take a look and get into this. So here we go. Whoop, don't fall. Here we go. We'll come back to you in a minute. Alright, here we go. Now, okay, this is a meter stick. And by the way, here's a review of metric conversions. This is 1 meter. This is 1 meter. Now, let's do a little review. See these little tiny little thingies right here? See these right here? Those are millimeters. There's 1,000 of these millimeters in 1 meter. See these right here? 90, 91, 92? Those are centimeters. There's, look here, 100 of these in 1 meter. Okay? Keep that in mind. This is 1 meter. Just a side little thing. All right. Class 3 lever. In class, we've talked about FIO. What the heck is a FIO? Well, here's what it is. F-I-O. Obviously, it stands for fulcrum input output. And we know that levers are an example of a simple machine which doesn't do the work for us, it makes our work easier. So let's take a look, and we already talked about in class, this is the input, this is the output. The input is where you input the work, or you put in the work. So if I apply a force right here, look at how this would rotate. And we know a lever is a bar that rotates on a fixed point, the fulcrum. So if I decide to rotate this and apply a force, right, it can swing about this distance. So I'm going to give that a little d, means small distance. Now, look out here at the output. If this simultaneously moves, see how this goes a small distance? Dude, look how big of a distance that's going. Oh my gosh, I'm like out of room. What's this? Big distance. Look at that sucker right there. Look. Whoa, 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 whoa. See that? So here I give it a big distance out the output where the machine finishes off the job. So if work is the same, we know that work is force times distance, or FD cosine theta for some of you. So just focus on force and distance. What kind, if you had to, like, say capital F was a big force and little f is a small force, how would you assign the forces for this to make the work the same? So what this means is, at the input, you would apply a big force over a small distance. And at the output, there is a small force applied over a big distance. But overall, the work is the same. It's a trade-off. So given that, we always use our visual mechanical advantage in general is output force over input force. So for output force, it's a small value compared to the input force. A smaller number over a bigger number mathematically is going to give you mechanical advantage of less than 1. So here's an example right here. And I can't play lacrosse, I can't play baseball, but like if I'm going to play lacrosse, this is where the ball gets shot right here. Here's the input. I don't care what you think about my form, I don't know how to play, but you get the idea. Down here is the input, here's the fulcrum. Boom, swing. Big force, right? Small distance turns into big distance, little force. Your arm, this is an example of a class 3 lever. Fulcrum, input, output. Again, when it moves, fulcrum, input, output. FIO. Okay? A fishing pole. Now we'll go fishing. Fulcrum, input, output. Whoa, there we go. Same idea. So a class 3 lever. Broom. This is an imaginary broom. Watch. Boom, boom, sweep, sweep, right? At the input, right? Small distance, big force turns into a large distance, small force. Again, the work, without efficiency ideally, is the same. So class 3 levers, FIO. With your fingers, look, FIO. Fulcrum, input, output. Small distance, big force. Big distance, little force. The force gets smaller, so a class 3 lever, less than 1, it multiplies. Multiples, yeah, I can spell. Multiplies distance because the distance gets bigger. Okay, I think that's a pretty good summary right there because you guys pretty much know what's going on. And you challenge science people that are only watching these 2 videos, you can figure this out. This is simple. Okay, so there's that. Okay, it's a class 3 lever. So put that down. Let's take a look at a class 2 lever. So we have FIO, FIO, FIO. I'm going to keep that up there. Now watch this. Let's look at a class 2 lever. Watch that. I'm going to write class 2 lever. You know what? Now, here's what I'll do. I'll make it even better. I'm going to put FIO, FIO, FIO over here. Right there. So now I'm going to put class 2 lever. And you know what I want to put next to that? I'm going to put IOF, IOF. What's an IOF, IOF? I know what an IOF, IOF is. Take a look. Lever. The bar. What does the bar need to become a lever? It has to have a fixed point. So I'm going to put the fulcrum, right here. That's the pivot point. I'm going to put the input here and the O here. Look, IOF, IOF. How many times that's IOF? 2. Class 2 lever. Brilliant. So now watch this. So if I apply an input force out here, watch this. Right? Or it can go this way. Well, usually it's going to go that way. It's going to lift the object. This right here goes a smaller distance. So look at the big distance out here at the input. Smaller distance at the output. Okay, so it's F times D. Machines, it's always a trade-off. Work is about the same. So if I had to assign the forces out here with the big distance, you apply less force. Here, where the masses get lifted, you want a big force. Okay? So notice here, from input to output, mechanical advantage for class 2 lever, we look at output force over input force, right? The output force gets a big F. The input force gets a small f. Bigger number over smaller number is always going to give you greater than 1. So this machine multiplies force. Is that clear? So again, here's an example. A wheelbarrow. Now, here's the fulcrum down here. Here's where the material gets lifted. Here's the handle. I don't know if you can see this. Hold on. One-man production show here. Watch this. Watch this. Cameraman and actor. Watch this. So like here, I'm going to use this. Look at this. Creativity right here. Hold on. That is the fulcrum. Here, watch this. Get in there. That is the load, that the output. This is the input. I can't lift that. It's too heavy. I can't do that work. Class 2 lever, will you do the work for me? You know what the class 2 lever says? Nope, I ain't going to do the work for you. I'll help you do the work. What do you mean, class 2 lever? Do it for me. Says, no, I'll help you do it. I can't apply enough force to lift up that box of tissues. Okay, well, you'll apply a force, but it's smaller, but you got to apply it over a longer distance. Longer distance, and I'll apply a bigger force over a shorter distance. So watch this. Whoop. Whoop. So then right here, hello, my hand right here, see this? This is the big distance. Right here where the tissue box is, that's the small distance. Force gets multiplied. Where's the fulcrum? Down at the wheel. So again, look at that. Wow. Can you see that good? Hold up. There we go. So now watch this. Again, watch this move out here. Big distance, little force. Turns into little distance, big force, and there's the fulcrum. IOF, IOF. Do yourself a favor tonight. A door is an example too. Besides a wheelbarrow, you can also have a door. Go home tonight and open up a door next to the hinges. See how hard that is, because when you open it, it's a small distance, big force. Where the handle is, it's on the end, far from the hinges, that's the input, large distance. The output is like next to the hinges, and the hinges is the pivot point, the fulcrum. So open the door near the hinges, hard to push, big force, little distance. Open up by the handle, much less force, but the trade-off is you're going a larger distance. Okay, so class 2 levers have a mechanical advantage of greater than 1. Again, work is the same. It's a trade-off. Ideally, I know there's friction and efficiency, but it's a trade-off. Machines make work easier. All right, so let's erase this. All right, now, here's where the fun starts. So you got class 2 lever, FIO, class 3 lever. Class 1, IFO, good old IFO. So think to yourself, what does IFO stand for? Not hard, but here's where it gets interesting. Come on, evaporate. Oh, review. This board is going to evaporate. I'm going to add kinetic energy. I'm going to make the air molecules move fast around it, so therefore it's going to attack the water, and the water is going to evaporate liquid to gas at the surface. And the water that leaves is going to become hydrogen oxygen gas. It's going to be water vapor molecules, gaseous molecules, H2O in the gaseous state, moving all the way around. There's your chemistry review right there. Okay, nice and clean. It's evaporated. Oh, what was left behind? Dirty chalk. There's your review. Wow, look at that. Science is everywhere. Okay. IFO. Now, why do you got to pay attention? It's a big one. And by the way, we got the hand truck. We'll use you in a minute. So here's the first class 1 level. Watch this. IFO. Wait a minute, I can put the fulcrum anywhere? Oh snap. I'm going to put it right here. Right in the middle. Hold on. Won't be getting better. Right in the middle. So watch this. Forget about output force over input force. If I were to, let's say, push down a distance with a force, F and D, what would this do? Go up the same distance with the same force. They're very similar. Why? The fulcrum is exactly in the middle. So to find mechanical advantage, watch this. I'm going to say this is a total of 10 meters. 5 meters here, 5 meters here. So to get the mechanical advantage of a class 1 lever, I know it's frustrating, but when you watch it, you can watch it over and over again. You take in the numerator the length from the fulcrum to the input force divided by the length of the fulcrum to the output force. So wait a minute, the forces are the same, the distances are the same. What's changing? Wait a second. What's 5 divided by 5? Mechanical advantage is 1. Oh, that's right. If the lever has a mechanical advantage of 1, it's not multiplying force, it's not multiplying distance, it is changing the direction of the force because it's right in the center. Does that make sense? The forces are changing the direction, just like the single fixed pulley. Very easy. Okay, so that's the first IFO. Now, watch this. Same 10 meters. Why did I do that? Why can't I just, sometimes I don't think. Okay. Whatever. Okay. 10 meters. Okay? Output over here again. Evaporate. Add heat to the system. Kinetic energy. Movement of molecules, 1/2 mv squared. Input. I'm going to move that fulcrum. Let's go this way. Okay? Now the length is still 10 meters, but I'm going to say this. This is now 8 meters. This is now 2 meters. So now here's your prime example. Okay, now watch this. Let's move the camera. Again, cameraman and whatever. Here we go. Now hold on. This is live action right here, man. Look at this. Uh-oh. Hold up. You're witnessing a person with no common sense on how to work a camera, but who cares? The effort's there. Okay. I'll even lift it. Okay, this right here is called a hand truck. Right here, you know what I'll do? I'll bring it up. Watch this. Boom. Here we go. Watch this. Oh, come on, man. Oh, zoom out. That would help. Duh. Okay, here we go. Now, let's say, oh, here we go. Oh. I got a big, heavy box of papers to lift. Oh man. I can't lift it up. Class 1 lever, will you do the work for me? No, I will help you. Okay. So now what do you notice? Let me see the camera. Okay. Now I'm going to stand here. Here's the input. Watch the heavy load get lifted. Here's the output. Output to fulcrum. Fulcrum are the wheels. Watch this. Man, I can lift that with one finger. That is so easy. Notice the distance that platform goes. A small distance must be a lot of force. And then if you look up here, hold up. I pull with a big, whoa, geez, big distance, little force. I can easily lift that box of papers up. So therefore, go back to my chalkboard. Notice there's no smartboard use here. Don't need it. Okay. So now, with this, right, I apply a big, there's a big, oh, sorry, big distance, little force. At the output, little distance, big force. So obviously, we know the mechanical advantage will be greater than 1. So the mechanical advantage, a hand truck by the way is the example, is the length of input over length of output. So the mechanical advantage is going to be, look here, 8 meters, input the fulcrum, over 2 meters. Mechanical advantage is 4. So a class 1 lever with the fulcrum closer to the output is greater than 1. Just think. Info, okay? So now, does that make sense? And finally, the last version of this. Let's take a look. Because the bell's going to ring in about 3 minutes, and I have limited time. And I get to give a pop quiz in a minute. Okay, so now, come on, evaporate. Look at the gas at the surface. Let's go. Physical change. Phase change to physical change. Here we go. Okay. Now, here's the bar again. Whew. Okay, here's the input. We're still in info. Here's the output. Well, what if I put the fulcrum right here, dude? Check that out. Oh, crud. Now I gotta like, small distance, big force. Oh, man. Because look, it goes a small distance. Guess what's going to happen? This object goes a big distance with a little force. Okay, now check this out. We're going to turn this around. We're going to make a trading check. Watch this. Come on. Zoom out. Yeah, perfect. Okay, now, here's the fulcrum. Here's the fulcrum. Now here's the output. Here's the input. Now if you notice, hold on, can you see that platform real quick? I want to make sure it's good. Okay. So when I said at the input next to the fulcrum, it's a small distance, big force, whereas this is the output, large distance, little force. Watch this. That sucker goes way that way. So again, watch again. Hold up. Little distance, big force. Big distance, little force. Work is the same, ideally. Oh. Okay, so again, the opposite effect. And with that, let's be consistent with our numbers to make this understandable for mechanical advantage, and I gotta go. We said this whole thing is 10 meters, right? So the length of the input is gonna be, we'll just say 2 meters. The length from fulcrum to output is 8 meters. So to get the mechanical advantage is, watch this, length of input over length of output. So the mechanical advantage is going to be 2 meters over 8 meters, because we have total 10. The mechanical advantage, reduce your fraction, 2 divided by 2 is 1, 8 divided by 2 is 4, is 1/4 or 0.25. So if the input's closer to the fulcrum, the mechanical advantage is less than 1. Why? Because what's getting bigger from input to output? Not the force, but the distance. So this multiplies distance. Okay? So again, I hope this was helpful. I try my best to make this understandable. It's easy, but there's a lot that goes into it. But if you just think and think about the distances, assign the little d and the big D, or the whatever, and then fill in the forces accordingly, then you realize that work is a trade-off, and the machine doesn't do the work for you. It makes it easier. Okay, so again, we have the famous saying, IFO, IOF, FIO. IFO, IOF, FIO. Very easy way to remember the order of the input, the fulcrum, and the output. IFO, class 1 lever, I said it once. Class 2 lever, IOF, input, output, fulcrum. How many times did I say it? 2, class 2 lever. Class 3 lever, FIO. How many times did I say it? 3 times. Say it yourself 100 times, you'll know it. And then you should be good. All right, so I made a thing on ramps and on levers. I hope that helps. And you had other review too on evaporation and other things. Okay, good. All right, bye.